Welcome to HotChips 20. Session 7, Networking.
Okay, let's start with the next session on networking. Session chair of this session is José Renaud. Unfortunately, he cannot be with us here today, but he did put in all the work of preparing the presentations with the presenters, so my job is relatively easy. My name is Jan Willem van der Waard. I will do this session. The first speaker is from DS2. His name is Chano Gomez. He's a Vice President of Technology and Strategic Partnership, and he will be talking about a low-cost chipset for broadband power line communications. Chano?
Thank you. First of all, thank you for giving me the chance to present here today. Can you hear me well? Okay. So I'll move away. I'll give a brief introduction of what power line communication is for those of you who are not familiar with the topic, and what my company DS2 does in the field. For those of you who are not familiar with the concept, power line communication is a very generic technology that can be used for sending any kind of data over electrical wires. This can be used for a variety of applications, and what my company does, DS2, is we've developed the core technology and then try to customize it for different applications and for different markets. So probably the most interesting applications for power line technology today are these three ones here. The first one, actually the application for which the company was founded 10 years ago, was for developing access networks using electrical wires. The vision here was that there are many areas in the world where there is no availability of either telephone lines or coaxial cables or optical fiber. So, but in many cases there is already electricity. There are many countries in the world where the penetration of fixed telephone lines is very, very low, 10%, 5%. But significant parts of those countries have power availability. 80 to 90% of the households have electrical power. So it makes sense to try to use those wires for sending data and provide all kinds of services: internet access, voice over IP, remote management, etc. So this is the first application that we thought of, broadband access applications. The topology is a bit more complex than some of the applications I will mention later. Typically, you will have locations in the network where you have a broadband connection, either fiber or wireless, etc. And then you use different devices in the medium voltage line and low voltage line to provide connectivity to a neighborhood. Another application which is similar to this one, but it's combined with other access technologies, is what we call access extension. For example, using this to extend fiber to the building or fiber to the neighborhood networks. It's well known that in some topologies, deploying fiber all the way to the building, has a reasonable cost, but then trying to provide a fiber connection to each one of the apartments or the units inside the building is very expensive. So one of the popular applications is actually using power line technology to extend, for example, passive optical networks into individual units in a building. That's one of the very popular ones. A third application, which is again getting closer and closer to the end user, is simply use power line technology for home networking. The same way that you would use regular Ethernet networks, or you would use a Wi-Fi network to connect a PC to a router or to a gaming console, etc. You can use power line for that. And actually, there are already products in the market today. In the consumer market, you can go to Best Buy or Fry's Electronics and buy power line adapters that you can use for connecting your computer to a router or to a TiVo or a gaming console or any other kind of device that has an Ethernet connector. So that's the third major application. As you can see, each one of them, we get closer and closer to the home network. And usually they make sense in different areas. In those areas where there is no broadband availability, where there is no DSL or no cable, it makes sense to use power line technology as an access technology. In those areas where there is already a lot of broadband services, there is DSL or cable, fiber, etc., the demand from the market perspective is for more home networking devices. Once people have a broadband connection to the home, they will want to connect different devices inside the home to share that connection. So that's a market where it makes more sense to use power line technology for home networking. If you have never seen one of these products, they look like this. It's typically a small adapter that you plug into a regular socket, and it will have an Ethernet connector so that you can connect that to your computer or to a router or to any device that has an Ethernet port. The question that I get asked very often is, why would anybody use this instead of using regular Wi-Fi technology? And the response is that Wi-Fi technology works very well and is very convenient to use as long as you don't demand a level of reliability which is too high, or you expect too much coverage. And for regular internet access, Wi-Fi is great. I don't think you can beat the convenience and the price point of Wi-Fi technology for just sharing an internet connection or for mobile applications. But for applications that require very high bandwidth, like for example, delivering high definition video to different rooms in a home, Wi-Fi is not capable, at least Wi-Fi today, is not capable of doing that with the level of reliability that some service providers demand. For example, this chart here gives you an idea of which kind of coverage you can expect to get in a home when using power line technology or 802.11n technology in the 5 gigahertz band, depending on how much bandwidth you want. For example, if you just require 10 megabits per second with 0 packet loss rate, according to our own tests, and this is in European homes, which typically are a more hostile environment to wireless technology because of propagation issues with construction materials. With power line technology, you can guarantee 10 megabits per second in 100% of the locations in a home versus 75% of the locations if you use 802.11n technology, commercial 802.11n technology products, using the 5 gigahertz band, which is usually cleaner. If you demand 20 megabits per second, then you can guarantee that with Powerline in around 90% of the locations versus 69% for wireless. And for 30 megabits per second, you can guarantee that in 85% of the locations versus 60% of the locations when using wireless. So for applications that require very high bandwidth with very high reliability, Powerline has a lot of value to offer. For applications that are fine with lower bandwidth or with lower reliability, like regular internet sharing, Wi-Fi is probably the way to go. So Powerline transmitting data at very high speeds over Powerline has its own technical challenges. Some of them are similar to what you have with wireless technology, some are different. First of all, the important thing to take into account is that the environment is unpredictable. You have no way of knowing in advance how the power lines in a home are going to look like. Every home is different. Every home has, done renovations at different times with different kinds of wires connected to each other, and all kinds of devices being connected and unconnected at random times. So it's very difficult to know in advance how the environment is going to look like in terms of channel frequency response or noise levels. There is a strong impedance mismatch in the line, which causes reflections, which causes multipath effect, where a receiver will receive multiple copies of the same signal at different times with different attenuations. This has the effect of producing a non-flat channel. Also, so the channel frequency response is unknown, it's non-flat, and it's non-stationary. It will change with time. Depending on which devices are connected or disconnected, the frequency response will change with time. Also, you have electrical devices being connected to the network at random times that introduce noise, which is non-Gaussian, it's non-white, and it's not stationary. It's changing all the time. And also, you have issues because the wires are not shielded, because they were never designed for transmitting data. There is potential issues with EMC, with interference to services which may use the same frequencies. That's why FCC puts strict limits on how much power you can put in these lines, which means that because we have limited power, we have to deal with situations with limited signal-to-noise ratio. So how is the industry dealing with these issues? Well, if you look at the technical features of state-of-the-art power line communication systems, kind of more or less, all of them look very similar. All of them use frequency bands in the 2 to 30 or 32 megahertz band. You cannot use lower frequencies because they are very noisy and they're also used for AM radio. And you cannot use much higher frequencies because the FCC limits don't let you put significant power in those frequencies. So that 2 to 30 or 2 to 32 is kind of the interesting spectrum to use for this application. Most systems use some variation of OFDM modulation, multi-carrier modulation. The reason for doing that is that, as we will see later, it allows you to optimize the data rate to the non-flat channel. You will have different frequencies with different levels of signal-to-noise ratio and different interference levels, and multi-carrier modulation is the best way to optimize for that. Also, this is very useful for ensuring that you can reduce the power level in a specific frequencies so that you do not interfere with licensed radio services in those bands. For example, with amateur radio services. That's a very common question that I get. What is the effect of this on ham radio? Because in the past, many years ago, that was an issue. Most of the systems use a TDMA MAC as a way to share the bandwidth between different devices. The reason for that, for going to TDMA versus simpler CSMA modes, is that the most interesting application for power line, as I said before, is video distribution. So with video distribution, you have very strict requirements in terms of latency and quality of service and allocating bandwidth to specific data flows. So TDMA architectures are the most optimized for that. The PHY data rate, or the marketing data rate, as I like to call it, all of them are around 200 megabits per second. We're very proud that our company was the first to deliver a chip at this speed, and then other companies followed that path. This is the data rate at the physical layer without taking into account all the overhead of error correction, etc. Once you take that into account, the maximum application data rate that you can get is around 120 megabits per second. That's in the optimal situation. In real life, you will get lower than that because you have different kinds of noise levels and attenuation, etc. And then, in order to ensure privacy and security, most systems already employ some kind of AES encryption, either with 128 bits or 256. So this is a picture of how the state-of-the-art power line systems look like, not only the ones provided by DS2, but also from other vendors. So what is special about the power line channel? How do we deal with that? That's the purpose of the next slides. As I said before, because in power line we have impedance mismatches, we have signals that end up with unterminated impedance, so we have reflections and echoes, and the receiver usually will get several copies of the same signal with different delays. So depending on the frequency that you're using and depending on the delay of those echoes, you may end up with either constructive interference or destructive interference. The same case as in many in wireless systems. So for example, if you send two signals, the blue one and the red one, in this case, because of the specific delay and the frequency, they kind of help each other to get a stronger signal. So in this case, in this frequency, you will get a stronger signal thanks to the multipath. But in this other case, they are in different phases, so the actual output signal, the red one, is smaller than any of the two original ones. So in this case, the signal will be weaker, and it will not that frequency will not be very useful for sending data. So once you look at the whole spectrum that you're going to use, this phenomenon is changing in each frequency. So if you look at how the signals look like when you transmit them over the power line, the transmitter will send a signal which has a very clean spectrum, flat spectrum from 2 to 32 megahertz. But after the signal has traveled through power lines with all those reflections and echoes, etc., you end up receiving a signal that looks like this, that has a spectrum, with notches and peaks and valleys. You will have frequencies like here where the signal is weak because of the destructive interference, and then signals here frequencies where the signal is very strong. In addition to that, you also have a background noise at the receiver, which is not flat, and it's not wide. You have different frequencies with different noise levels. So if you can combine them together, you can see the received signal here in green versus the background noise in red. And the useful metric here is the signal to noise ratio. What is the difference between the green one and the red one at each frequency? Because we will treat each frequency differently. It's well known that the maximum data rate that you can put in a channel is depending on the signal to noise ratio that you have. So when the signal to noise ratio is high, we can put high density modulations. When the signal to noise ratio is very small, we'll have to go to smaller modulations, as described in this diagram. So when the signal to noise ratio is high, you can put this high density QAM modulations. When the SNR is low, it's difficult to demodulate the signal. So what the devices do, what Powerline devices do is, when presented with this information, with the receiver power level and the noise level, and they calculate the SNR, which is this graph here. This one is the difference between the green one and the red one. This is the interesting metric here. And what the device does is, for each frequency, it calculates what is the maximum modulation scheme that can be transmitted reliably. So you see that in some frequencies, the modulation level in each carrier, in this case, is very high, and in this case is medium, and in this case is very low. And you can find situations where there are frequencies where you cannot transmit any data at all because it's too noisy. So this is the basic fundamentals of how the physical layer in a Powerline communication systems work. We estimate the SNR, and we determine the modulation scheme for each frequency. And we have to do this continuously because this is changing with time. This can change every few seconds. So all the time, the devices need to retrain and agree on new modulation schemes to make sure the communication is reliable. This is a simplified block diagram of how a Powerline modulator will look like. You have the data stream that you want to transmit. Typically will be Ethernet packets. You divide them in smaller chunks. You add some error correction. In this case, we're using Reed-Solomon. And then these blocks here basically put the data in the specific carriers. Then there is a four-dimensional trellis code modulation. We modulate each one of the carriers. We do an inverse fast Fourier transform. And then we generate the time domain signal, and then we put that into the line through a D2A converter, analog front end, and then we put it in the line. And then the receiver will do the opposite. So this is related to the physical layer. Another interesting thing for Powerline communications is, as I said before, because one of the most interesting applications is video delivery, it's very important that the technology can handle QoS effectively, especially in situations where you may have video and voice and data simultaneously, and you need to be able to give high priority to one application versus the other. One of the interesting things in the markets that we're trying to address is that in many cases, the data flows that you want to handle differently do not come with the right QoS tags. There are standards for QoS tagging. You can use 802.1p at layer 2, or you can use a type of service or DSCP field at layer 3. This is very useful when the data flows that are getting into your network actually have already been tagged with the right information, or have been pre-classified with the right information. The problem is that in many cases, we don't have that luxury. We have flows getting into the network with no information about which one is high priority or low priority. So it's very important for a network device to look for additional rules to classify the packets. So the devices need to figure out how to assign priorities with limited information. So after talking to many customers and seeing different usage scenarios, we found out that every customer wanted to do this differently. There was no single rule that would work for everybody. So we decided that we wanted to have a programmable QoS classifier inside the chip, so that each one of our customers could use that in a different way. Some people would use that to classify packets based on layer 2 information. Some people will use it using TCP information or UDP information, layer 4. So we just provided programmable rules and let our customers do that. So in practice, what you can do with our system is you can kind of write rules like this. You can make the chip look at each one of the packets before transmitting the data and say, okay, if the Ethernet type tells me that it's an IPv4 packet, then if the destination IP address is this one, then the priority in the Powerline interface should be 6. Otherwise, should be 1. And if this first rule didn't match, then look at the Ethernet VLAN tag. And if the VLAN tag is 5, then the Powerline priority is number 2. So this is the kind of rules that our customers wanted to build. So we provide that functionality in the chip. In practice, you don't use this pseudocode. You actually have to program registers to do that. And the way it looks is something like this. The Powerline chip can look at the whole Ethernet frame. This is the whole Ethernet frame with the 802.1q header, Ethernet header, IP header, TCP payload. Because we have access to the whole packet, we can look at different offsets in the frame and use that to create rules. So for example, here we can look at offset 0, get this information, mask it, and compare with a pattern. And if it matches, then we trigger this whole process here where we go to a second part of the frame, offset 1, get some other piece of information, mask it, and then compare it with different patterns. And from that, we get different varieties. So for example, with this, you can do things like if the packet is an IP, is a TCP, sorry, if it's a UDP packet, for example, by looking at the IP header, then look at the UDP port number and classify the packet based on UDP port number, for example. And you can create many different rules within that. The product that we provide to the market that implements this is a chipset that we announced recently. It's called the Aitana chipset. Aitana is the name of a mountain very close to Valencia, which is Valencia, Spain, which is where the company is located. So the chipset this chipset is the core required to build a Powerline-to-Ethernet bridge, which is basically a product that I showed you before, which is a small box with an Ethernet port on one side and a power line connected on the other side. What you need to build that kind of device is basically our two chips, the 9101 PHY MAC network processor, and then the 7800, which is an analog front end. The PHY MAC chip has an MII interface, so it can accept packets from an Ethernet interface. It uses external flash and SDRAM. It has control for controlling the user interface, like buttons and LEDs, etc. Then it has a transmit and receive path that communicates the digital chip with the analog chip. It has an SPI bus so that it can control the analog chip, specifically for changing the gains of the programmable gain amplifiers. And then you have some filters, combiner, and then the AC line here. Here you have the 110 volts or 220, depending on the country. So this is the basic building block for a small Powerline-to-Ethernet adapter. If we get into details of this chip, the 9101, it's based on the UPA standard. UPA is Universal Power Line Association. It's one of the 3 competing standard organizations to have a unified power line standard. The chip is an LQFP 126 pin. Power consumption is around 1.2 watts, and the voltage is 3.3 and 1.5. The modulation, the physical layer information is similar to what I mentioned before. It's an OFDM system with 1,500 carriers in a spectrum from 2 to 32 megahertz. Each one of the carriers can be programmed. You can attenuate the signal in each one of them so that you can change the spectrum of the signal. This is very useful for compliance with the regulation in each one of the different countries, because different countries have different regulations regarding this part of the spectrum. Error correction is done with Reed-Solomon and Trellis code, and it can handle up to 16 remote devices. There is a limit on how many remote devices you can talk to, and the reason is because the modulation parameters are different for each connection, you have to store that in memory. So that's a major limitation. Data rate is up to 200 megs per second physical layer, 120 megs per second at the Ethernet layer, and it is limited to 128 kilo packets per second. So when you use very, very small packets, like 64 byte packets, the performance will be a bit lower. It has an embedded Ethernet switch, complying with the 802.1d standard and supporting spanning tree protocol. It supports VLANs. The forward table has 32 MAC addresses. It can do packet snooping, which means sending special packets to the processor for processing. We do that for doing IGMP snooping, etc. And it also supports automatic repetition, which means that each Powerline device can receive the signal from another device and regenerate it and send it to a third device. So you can create kind of like a mesh network where you can extend the coverage of the network by putting repeaters. The system supports encryption of AES 256, 128, triple DES, and DES encryption. This is for compatibility with previous generation devices that only supported triple DES, and supports security, which is set up just pressing buttons, which is a more convenient way for consumers than having to type passwords or remember passwords. From the point of view of QoS, it has 8 priorities and programmable prioritization rules, like I mentioned before. You can put the packets in the different queues according to programmable rules. It has an embedded processor, which is required for control messages, etc., based on an extensor processor from Tensilica, running at 160 megahertz. And we provide a software development kit that our customers can use to change the software that runs on the processor. The interfaces of the chip are one MII interface, 2 SPI. Well, you can see all the options here. And it's based on a system-on-chip technology from Toshiba. And the chip has been designed by DS2, except for the converters and the PLL, which were provided by Toshiba. By the way, the converters are inside the digital chip, as opposed to having them in the analog front end, which is the other typical partition done in the industry. This is a block diagram of the chip. The central unit is the bridge that forwards packets to the right interface. It has the modulator, the OFDM modulator and the converters here, interface with memory, interfaces to the analog front end, etc. The MII interface for sending and receiving data, JTAG, and a serial interface. The interesting thing is how the packets flow through the chip. This diagram shows how it does that. Typically, when the packet is transmitted from an Ethernet port to a Powerline port, it will go through the MII interface to the bridge. We will receive the packet. Optionally, we will tag them for later processing. I won't get into detail of that. It goes to the bridge that decides what to do with the packet. Should it be sent to the processor? Should it be sent to the power interface? Should it just ignore it? This is done using layer 2 information. Then it goes to the service classifier that decides the priority of the packet, puts that in the right queue, and then when the time is right to transmit the data, this block will build the MAC frame, reading the packets, high priority packets from the buffer, will encrypt them, will wait until the device can transmit based on the information from the MAC, and then we'll modulate it with the right OFDM parameters and send it to the analog interface. The system supports many different modes. For example, the one mentioned before, from sending a packet from Ethernet to Powerline, or the opposite direction it should be from Powerline to Ethernet. In this case, it goes from here with the modulated, goes to the bridge, and then back to Ethernet. Also from Powerline to Powerline, like receiving a packet from the network, demodulating it, deciding that the packet is not addressed to myself, it's addressed to somebody else, and then send it to the interface. How much time do I have?
You don't have any time.
Okay.
Could wrap it up. Okay,
yeah, so I think it will be shorter. This is the analog chip, which basically is a transmitter and receiver in one chip. It has the low-pass filter and the line drivers for putting the signal with the right voltage. And then at the receiver, when it operates in receiver mode, it has an external reception filter, low noise amplifier, low-pass filter, and then it goes to the analog converter. From the point of view of performance, this chip provides up to 20 megabits per second in the optimal conditions versus 90 megabits per second from one of our major competitors for different attenuation levels. In a typical home, you will have around 40 dB of attenuation. Here we're testing at 30 dB, 50 dB, and 70 dB, which is a very extreme case. And in all those cases, we still get higher performance than the other competitor. And this is the last one. This chip is based on a specification developed by the UPA, the Universal Power Association, that works at 200 megabits per second. UPA is working on a new version that will work at 400 megabits per second. We have already started doing some demos. And there is another association called the Home Grid Forum, which is working on a specification that will work at 1 gigabit per second and will transmit data not only over power lines, but also over power lines, phone lines, and coaxial cable, so that all the 3 kinds of wires in a home are unified. That's all. Thank you very much.
Okay. Thank you.
Thanks. Sorry for the time.
That's okay. Just less time for questions. So we have 1.5 minutes left for questions. I guess there's 1 or 2. Go ahead.
Bob Masley, Sun Microsystems. How do you bypass the power line pole transformer with the large insulators?
Okay. You don't do it. Actually, what you do is you put a device close to the transformer with 2 of these chips. One is connected to the medium voltage line, and the other is connected to the low voltage line. So you receive the signal from the medium voltage line, demodulate it, and then send it to the low voltage line using a different chip. So you actually take advantage of the fact that the transformer is there and provide some isolation between both sides.
Okay, any other questions? I would like to defer to the break after this session, or I guess the next section. Organizing committee reminded me to remind you to fill out the evaluation forms. Next session is from Cisco, 2 speakers. I guess they figured out that we're giving away 3 lasers, and now they're showing up with 2 people. Will Eatherton, who came to Cisco in 2000 from the startup Growth Networks and is currently director and distinguished engineer leading the software development for QFP-based products. And the second speaker in this section is Don Steiss. He led the high-speed logic design and processor design for 15 years at TI and is currently a principal engineer at Cisco. Will?
Test. Okay. Hello. So let's see. So before I get started, I just want to start with a little bit of an overview that the QFP packet processing chipset, which is actually targeted for a range of router and security appliance and so on devices, is probably, or not probably, is the most ambitious chip development project that Cisco's undertaken, both in the length of time, the how we went about it, and also the investment and staffing. I think at the peak we had around 150 folks working on the first generation of this chipset, on just the core chipset, and probably another 100 involved with the system ASICs that integrate this into router type devices. We also, as far as how we went about it, it was a time frame of multiple years. Cisco typically likes to start a project and see something that's in the lab and heading towards production in 18 months. And this development process is not, high-end silicon development like this does not match that kind of time frame. So there's a number of firsts within Cisco for this project. So I'm going to hit a little bit about the architecture, the sort of networking aspects of QFP, and the software side of the chipset. And then Don's going to talk about more of the hardcore silicon details. So the first thing, just to give you a little context, we shipped the first product based on the quantum flow processor chipset in May of this year. And as a vertically integrated company doing, from the chipset up through the software and then delivering the final product, we of course don't want to announce our silicon until we're actually shipping the product. But the chipset powered on, a year before that. And this, the ASR1000 is the first system based on the quantum flow processor. And it's, just to give you, I think it's a 2-slide overview, it's a mid-range router, edge router, and it has functionality, of course, the typical service provider gets into broadband environments, but it also, increasingly, we're seeing a lot of push for, security, voice, a lot of devices that were, previously or still are appliance-based, increasingly being, melded into the router. And so from a feature functionality, that was the kinds of requirements we had in the quantum flow processor design, is needing to be able to handle those range. So as a router, Cisco, of course, we have a wide range of different form factors and architectures. This device is what we call centralized type architecture. From a packet flow standpoint, there's the various L2, Ethernet, ATM, and so on, port adapters, and those are plugged into, depending on the form factor. We have 2RU, little blades up to systems that get into the 6RU today. And so there can be a range of those port adapter densities inside a box. The actual forwarding architecture for the ASR1000 is centralized in that all of the packets will flow through one quantum flow complex. And it's a standby active architecture, so the forwarding processor engine here is replicated, both the active and the standby, and then there's the failover and so on, and that can also be used for in-system upgrades. And similarly, there's a route processor complex. And I'm going to talk a little bit more about that on the next page from a software architecture standpoint, but clearly in this mid-range appliance and higher, from a software architecture and hardware architecture, we aren't trying to meld everything into a homogeneous set of processors. We do separate, high-end, doing routing protocols, table compilation, management management and user interface into functionality that goes on a route processor. And then what we're really doing in the forwarding engine is all the functionality that touches packets. Now, this previously, a few years ago, mainly meant modifications of the packet for forwarding, access control and so on. Now, in really where this has been going as far as merging security, voice, all these applications, this involves things like deep packet inspection, which can involve regular expression matching. It involves IPsec types of features. It involves intrusion prevention and session border controller functionality. So it looks a lot more like general purpose processing as far as needing to be able to update session state and so on. To put that into a software architecture overview, the route processor I was showing, from a software standpoint, we're running Linux, and then we have the iOS operating system running in a Linux process. And we then have forwarding manager running on the card that's also Linux process. But at the bottom of the software stack, the QFP software, the key things to take away on this is it's not a kernel based. So it is ANSI C. We do have memory management, all these types of functions. But when we went through from a architecture programming model standpoint, the benefits of actually running a kernel didn't make up for the sort of overhead from performance standpoint. And so from a software architecture, it is more of just ANSI C object code that is then running into a loop. The other key aspects, again, is that things like having a routing table compiled, that we don't really want to optimize to put onto the quantum flow processor itself. So that would reside in the upper layers of software. Taking in rules for classification and compiling that would happen between the iOS layers and the forwarding manager. But then at the lower levels, we are doing anything where we need to do state modification on a per packet basis, and even over time things like TCP stacks and so on, that would need to reside in the QFP software. So this is the overall architecture, and I think the basics of a data flow and a router or a chipset can look, if you abstract enough, it'll look very similar regardless of the chipset. But the key points for the QFP is that we do have 40 1.2 gigahertz processor cores. Each one has 4 hardware threads, and therefore there's 160 packets being processed simultaneously, and that is instruction level interleaving. Each one of those processor cores has a common view of global memory and other resources that are attached. There is no assignment of memories or interfaces to processors. It's a pool available to all of the processor cores. From a packet flow standpoint, packets will enter and will be really distributed on a who's available kind of basis. And a key architecture point was we very much wanted to have the programming model be as simple as possible. So we use a run to completion programming model. We don't do flow-based load balancing, and we really, when it comes to then how are you, all the various coherency and flow ordering, that's things where we've built hardware blocks that assist with managing those data structures and tried to make that as simple as possible from a software standpoint so that they're all accessing global table, and we've tried to, we've looked very carefully at our applications and tried to minimize the load on the software programmer. So there's actually, when it comes to the feature code that's running on a PPE, we typically do some optimization, but at the core, it actually is something that can be run on a general purpose processor on a single core kind of thing with some acknowledgement to the fact that it's multi-core, and that has to be taken into account through various library calls that will then pull in the hardware blocks in order to help deal with that. The other key points from memory standpoint, we're using RLDRAM2 technology. We do have TCAM interfaces. The total memory bandwidth across all of the queuing, scheduling, and all of the resource DRAM comes into, I think it was 400 to 500 gigabits kind of range, so 60 gigabytes kind of area of total memory bandwidth. So through the architecture, there was a number of trade-offs we had. We have a number of internal network processors. Cisco's probably used every startups, or at least evaluated every startups. We have a lot of experience with, assembly code. We have, models. We also have experience with the instruction memory and so on. So we came away with a number of before we even started the architecture, we wanted to have a high-level language. Along with that, we didn't want to worry about slotted memory accesses or having to count those kind of cycles. We wanted to, from a ISA standpoint, we wanted to have high quality compiler support. We ended up evaluating a number of options and chose the Tensilica ISA in order to leverage some of their tool flow on the back end. And then from a latency hiding standpoint, I mentioned earlier we want the programmer, at the end of the day, he is aware of when he's coding a feature like firewall, for instance, he's absolutely aware of the fact that he's coding for QFP, but a lot of the code is portable, and we did not want to have to get into explicit latency hiding. So things like the 4 hardware threads, and that really being something the hardware hides from software as far as interleaving accesses across the different threads, that was something that we wanted to simplify from a software standpoint. We also spend a lot of time on accelerators, what should go into hardware, software. One thing working with a large hardware team of very motivated folks is there's always a lot of excitement about putting everything into hardware. We evaluated many different accelerator options. We ended up trying to do it very quantitative. So at the end of the day, packet processing scales very linearly. So we tried to quantify everything in terms of how many processor cores. So if we're going to put in, let's say, a regular expression engine, how many processor cores are we trading off? And then what type of feature mixes and how important to our end customer is having the regular expression versus that additional, 2 processor cores? And that's the kind of trade-offs we did. We came to some conclusions that 2 areas we did want to significantly offload from software were crypto and scheduling. So just hit those a little bit more. Scheduling, packet scheduling, which the traditional and really core function router, is very interesting in that it's difficult to parallelize. All the rest of the applications we deal with, it's very easy to isolate, have critical sections of code, access to global databases, and not have to think too much. Scheduling is something that's very tight with real-time constraints, and it's very difficult to parallelize. So we ended up throwing a pretty significant hardware development at the traffic management scheduler portion of this, and that was one of the largest developments that we did do from an accelerator standpoint. The other one was bulk crypto. So if you look at a feature like IPsec, all of the packet inspection, dealing with the sequence number, all those kind of things, it makes sense when we want to have in quantum flow software. But on the other hand, the bulk, doing the SHA and so on, was not something that we really felt that we did look at putting pieces of that in, but at the end decided that's something we wanted to offload to third-party silicon. There were other trade-offs. In the end, we didn't, for instance, put regular expression matching. We put lookups. We put some lookup algorithm hardware and other things but we didn't, in my view, go overboard on a lot of those fronts. The traffic manager I just mentioned was probably the single largest hardware block. And the key thing here is that a device like this, I was mentioning it goes across appliances as well as service provider, broadband, and so on. And in a lot of the service provider broadband markets, the customers have come to have very let's say very strict expectations from Cisco on the QoS delivery. So things like the number of queues, the numbers of levels of priority, being able to set all these little knobs, having 5, I've been hearing about 7 layers of hierarchy where you would want to have a packet, you being able to configure on whether it's classes of service passing through individual sessions to ports, physical ports on the box. All of those need to have their own levels and be able to set parameters. So this is something that we did invest a pretty significant area on from a hardware standpoint. But at the same time, we wanted to have a lot of configuration of being able to configure all these nodes from a software standpoint. The software code development and debug, just a couple things to note here. The first one is that there was a very significant effort on putting a simulation environment and a tools environment together. And actually, one thing I'm very happy about, sort of how this staffing happened within Cisco, is we put the architecture team and the tools team together first at the very beginning of the project, and that really enabled us to do things like put together a IDE Eclipse-based environment for the development, and have that so it can hook up to a simulator, it can hook up to the real hardware. It has actually, we've had folks do comparisons with both other network processors as well as just various tool sets that are in the industry, and it compares quite favorably, and it also pulls together all of the compiler, assembler, and all these kinds of aspect into one environment. So what that's really enabled us to do is a couple things. It enabled us to do very quick development, but it also has enabled us to deal with things like coherency as far as being able to put in checks into the simulator and have the simulation environment help us catch coding errors, this kind of thing, without having to have that be a trial and error kind of mode. And just to give you a quick feel, this is the kind of environment I was mentioning. You can do, of course, code development, but you can also do breakpoints and watches not only in the processor core, but in a lot of all of the side memories, the accelerators I was mentioning. There's visibility into those blocks, whether it's the simulation environment or the hardware environment. And this is, once again, I mentioned this is an ambitious program, and the tools environment is something that's been very important. Unfortunately, this is not something Cisco ever plans to really expose externally. This is an internal development environment, but it's been an important part of the overall program. So with that, I'm going to hand it to Don here.
So, need that. So the remaining slides are more on the implementation details, how we put the thing together, some of the trade-offs we made, and some of the results that we obtained. Trade-offs in memory system, ordering is a big deal. You can expend a lot of verification energy, a lot of hardware, a lot of time working on architecture on that. We ultimately decided for the type of application that we're doing, we were not justified in building a strongly ordered or providing much order in the way of loads and stores. So there is no load and store order guaranteed for multiprocessors. We do provide some barriers and indivisible operations, and we do have some atomic ordering that Will mentioned that go along with the packet state. The data cache parameters, obviously more is better, but we really wanted to fit a large number of these processors on the chip. So you want to put as much as possible, but you really can't. You really just want to cover the parts of the working set that have high locality. And in our case, that tends to be just the stack. Instruction cache is similar. Obviously you want as large as possible. We ended up with an architecture with a large second level cache and a moderate first level cache. We do have a pretty extensive communication network on the chip that's used for processors to communicate with memory and to communicate with these hardware accelerators that Will mentioned. Ultimately, everything turns into messages. Anything that looks to the programmer like an address mapped space is actually converted on the fly into messages, and that's sort of invisible in the programming model. I'll skip over this. This is an example of examining a resource state. These are the two chips in the chipset. The left chip is the packet processor. The 40 processor cores, that's one right there, and it's about 4,000 microns wide, about 590 microns tall. It's a nice regular looking object. This area here is an array of 8 crossbars that connect groups of processors to the resources. There's a large second level instruction cache at the top there. That's 512 kilobyte instruction cache capacity. Around this chip, the largest consumer of IOs is 8 DDR2 DRAM channels, each running at 400 megahertz. It's built in TI 90 nanometer, 8 levels of metal, lots of transistors, lots of IOs. There is an 800 megahertz DDR interface that connects these two chips, sort of a high bandwidth interconnect between the traffic manager and the packet processor. Traffic manager is 400 megahertz, like the synthesized portion of the packet processor. Enormous amount of SRAM consumed by queuing and various other activities. Each of the packet processing engines is shown here. I'm not really explicitly showing the threading in the picture. There's a 4-stage instruction fetch pipeline, instruction queues that hold a sequence of partially decoded instructions for each thread, an execution pipeline that includes a thread interleaver that's doing a cycle-by-cycle determination of whether or not a thread is runnable, and then just doing a round robin over the runnable threads. Read, execute, 2 additional cycles for memory operations, and a write back stage. There's a 16 kilobyte 8-way instruction cache that all the threads share. It is a hit under miss cache. I can have up to 16 outstanding transactions in flight. There's a 4 kilobyte 8-way first level cache for data, but it's sort of locked down 2 ways per thread. So effectively each thread gets 1 kilobyte of cache space, primarily for the stack. There's a collection of hardware managed buffers, prefetch buffers, write buffers, read buffers, outgoing command buffers, incoming response buffers. And then there's the message coprocessor I mentioned earlier, which has 5 channels per thread. So each of these packet processors can have 20 data transactions in flight going out through the complex. The design methodology, a little bit on that. This was a customer-owned tooling or a COT design. We handed to Texas Instruments a completed GDS2 tape. One thing that was done, though, was they ran their complete suite of physical design checks on our data. And, you never turn down verification, right? This was additional verification that a parallel team did, and it turned out to be very, very beneficial to us. Outside the processor array, it was synthesis, place, and route, multiple commercial synthesis tools, and quite a bit of in-house RTL code generation to do that. The design methodology in the processor was cell-based, largely static CMOS, some selective use of domino circuits, schematic entry with physical specifications for instance names in the instance names for fast and deterministic placement. What that means is that we more or less quantized the size of our cells. The AND gates, came in a certain selection of sizes. But as far as the physical design went, we hand specified or algorithmically specified where every placement went. And the reasons for this are numerous, but the most important ones are the advantages that you get in power by controlling wire lengths. Speed is another very important thing. Repeatability, particularly when you are close to the limit of the number of channels that your technology can support, wiring channels. Being able every time to get a consistent result by very carefully placing the gates is quite important. Our belief is that as we go further down into smaller and smaller technologies, this is going to be even more essential as the parasitic get even worse. So I think that the days of sort of throwing it over the wall to a place and route team might be coming to an end. Polygon level artwork and some critical modules. For verification methodology, we have multiple functional reference models and used equivalence checking. A little bit more on verification. You guys can look at these later. Let's get to some results. Shmoo plot on the product, frequency on the bottom axis, voltage on the vertical axis. I hesitate to show this because there's apparently some subculture that is into taking apart the little blue Linksys routers and doing all kinds of exotic things with them. There's apparently a beefy MIPS core in there that we can do things with. Don't take apart your $30,000 router and try to overclock it. Not recommended. So as far as results go, on our Rev 1.0 silicon, Will mentioned this earlier. We delivered, actually we taped it out fourth quarter 2006, delivered it for integration onto the board 2007. First packets were through the production software February 2007. There was actually packet flow or demonstrated functionality with a sort of a verification environment earlier than that. We think this is impressive. Handing it off and letting customers play with it August of that year. And then as Will mentioned, we did the product launch on March 4th of this year. There was quite a bit of collaboration between the software team and the hardware team all throughout the design. Lots of arguing about, are you really going to use this instruction? Or are you really going to use this register? Because we wanted maximum density of compute function, and we didn't want to waste area on functionality that wasn't going to be used. And in the end, going back and studying this, all the mission mode registers and instructions were used. So I'm very happy with the software team. So in summary, router architecture involves a lot of subsystems with different requirements. You have subsystems that have embarrassingly parallel problems. You have other things like the scheduling problem, which inherently have a lot of dependencies. So there are many things that you have to take into account. Optimum architectures for different types of networking are still evolving. And a lot of what we do, since the ongoing support of a software team can be very expensive, support in terms of paying their salaries, a lot of what we do is trying to make things easier for the software team. That's very important to a lot of the work that we do day in and day out. So thanks for your attention.
Thank you. I think we have a few minutes for questions. Okay, no questions. That means we can make up on the schedule. So there's no break now, but